The new section is entitled Solutions about Singular Points. Now, suppose you have an equation of this form. Y double prime plus a function of x times y prime plus another function of x times y is equal to 0. Now, to be analytical at a point, it means the following. A function f is said to be analytical at a point A, for example, if it can be represented by a power series, PS is power series in x minus a. I guess we should say with a positive or infinite radius of convergence. Now, what does that mean? It means that f of x can be written as the summation of a sub n x minus a to the n, where n goes from 0 to infinity. That is, it's like a polynomial. For example, here is a polynomial, 3x cubed plus 4x squared plus 5x plus 11. And here's another polynomial, 3 times x minus 5 cubed plus 4 times x minus 5 cubed plus 5 times x minus 5 plus 11. It's similar to the one above, but notice the only difference is x is now x minus 5. They're not equal, but here's a power series in x equals 0, because each x is the same as x minus 0. That x, I can replace it with x minus 0. That x minus 0. So instead of the 5's, this equation here has zeros. This polynomial is in x minus 5. Now, if we kept going forever and ever, these would be power series. Here would be a power series, the top one, where x is 0. This will be a power series, where normally it's x minus x0 or x minus a. In the top one, a would be 0. In the bottom one, a would be 5. If it were infinite, if it went on and on. So that's analytical at a point. Now, let's talk about, say, an ordinary point. Because basically, we want to get to a singular point. What is an ordinary point? One can say that a point x0 is said to be an ordinary point of the safe space of this differential equation if both p of x, that p of x, and q of x are analytical at point A, or at x0. Analytical at x of 0, that point. A point x0 that is not analytical is said to be a singular point. A point x0 that is not an ordinary point of the differential equation is said to be a singular point. So we're going to be talking about differential equations, or how to solve differential equations about singular points. All that means is at the value x0, this and that, not both of them, can be written as a polynomial, a power series about x sub 0. One or both of these cannot be written as a power series using x minus x0. They both cannot be. Maybe P can, maybe Q can, but not both of them. Okay, so now we know what a singular point is, which is very important. Now, they're telling us for the next differential equation that I'm going to write, x equals 0 is a singular point. And they want us to find two linear dependent series solutions about x equals 0. And here is the differential equation. Now, just to convince you that x equals 0 is a singular point, I'll divide everything by 4x. I'll divide every term by 4x, and I get y double prime plus 1 over 8x y prime plus 1 over 4x y equals 0. Now, this is my p, and this is my q. And I claim they are when x equals 0 is a singular point. Now, the question is, you could ignore the 1 over 8 and the 1 over 4. The question is, can I write 1 over x as a power series where I have x minus 0? That is just in x. Well, we know that 1 over 1 minus x, so you should know this. This is the summation of x to the n, as n goes from 0 to infinity. Now, if I replace x with x plus 1, well, two things happen. The right side will become the summation of x plus 1 to the n, as n goes from 0 to infinity. I'm just replacing x with x plus 1. So I should replace x with x plus 1. Now if we do the arithmetic on the bottom, if you have 1 and you take away 1, you have nothing. That is, this is just negative 1 over x. So multiplying both sides by negative 1, you get the summation of negative x plus 1 to the n, and then goes from 0 to infinity. The problem is that's not x. This is, that argument here is really x minus negative 1. This is, so x equals negative 1, you would not say is a singular point. You would call it an ordinary point. And the same, so now if you really wanted the 1 over 8, well, I'll just put an 8 here and an 8 there. So this is exactly p of x. And likewise, instead of an 8, I can put a 4. And that's exactly p of x. But nonetheless, either one of them, whether you have an 8 in the bottom or a 4 in the bottom, this is a power series in x plus 1. We wanted it just in x. You're not going to be able to write it. So here x equals 0 is in fact a singular point. X equals 0 is a singular point. Now, these problems take a lot of space. So let's write it, the original problem on the top. And let's get going. We are going to assume that the answer is in the following step. So we let y equal, the solution y equal the summation of Cn x to the n plus r. Then the derivative of that would be, it's still a summation, but we take the derivative of Cn x to the n plus r. We bring down the power, multiply by the number in front, c sub n, make the new power n plus r 1 less. The old power 1 less. Now we take the second derivative. We keep that constant, n plus r times cn. We bring down the new power, and we make the old power n plus r minus 1 less. And then we take those new ways of writing y, y prime, and y double prime, and we put them here, here, and here. And the left side is equal to 0. So 0 is equal to the summation, is equal to 4x times y double prime, which is a summation. And since what's in front has nothing to do with n, I can bring it inside. In fact, when you're multiplying 1, 2, 3, 4 things by the 2 in front, the order you multiply is up to you. The 4 times n plus r times n plus r minus 1 times cn times that. Well, that's 1, the power is going to be 1 more than n plus r minus 2, but you're adding the 1. So we're going to get, and like I said, everything's after the summation now. So the summation of 4 times n plus r times n plus r minus 1 times cn times x to the n plus r minus 2 plus a half times y prime. A half times this. But the half can go inside the summation sign. plus y, which is easy. It's just the summation of Cn times x to the n plus r. Now, what I'm going to do is factor out x to the n. And when you factor out x to the n, all it's really going to happen is the n's going to disappear. You're going to have the summation of 4 times n plus r times n plus r minus 1 times c sub n x to the n minus 2 plus the summation of half of n plus r times cn times x to the n minus 1 plus the summation of c sub n x to the n. And n always is going from 0 to infinity. Now, I noticed that in the first two summations, they both go from 0 to infinity, and they have something in common. Now, we do have a little typo here. I explained that when we multiply this term by 4x, like it told me to, this power goes up 1. It should be n minus 1. Sorry about that. So now I have x to the n minus 1 in both. In fact, I have c times x to the n minus 1. So this I can use one summation. Summation as n goes from 0 to infinity. Basically, if you have the summation as n goes from any number to infinity, or something complicated like this, call it a, plus summation as n goes from the same starting number, whether it's 0 or 17, to infinity, or something complicated, call it b, maybe it's that. This is the same as the summation of a plus b as n goes from 0 to 100. And if there's anything common in the a and the b, well then you can factor it out in front or at the end. So this just becomes the summation of 4 times n plus r times n plus r minus 1 plus a half n plus r. And what I'm factoring out is c sub n x to the n minus 2. Now, let's not forget that piece. Okay, now I want to work on simplifying this plus that. They both have n plus r in them as a factor. So I can factor out n plus r. And then I have 4 times that, 4 times that, plus a half. We have n plus r times 4n plus 4r, 4n plus 4r, and then you have minus 4 plus a half. Now, I would love to write 4 with the 2 on the bottom, so we'll have the same denominator as the half. Well, 2 times 4 is what goes there, 8. So it's negative 8 over 2 plus 1 over 2, or negative 7 over 2, minus 7 halves. Okay. So we have x to the r, the summation as n goes from 0 to infinity of this, which is that, n plus r times 4n plus 4r minus 7 over 2. Cn x to the n minus 2 plus the next summation. Now, I would just love for the power of the x's to be the same. Call it k. I'd like for the power of the x's to be k. In the second summation, n just becomes k. The n will become k and n will become k. But here, we have n minus 2 equaling k. Well, if n minus 2, why am I insistent on messing this up? I said earlier how this is n minus 1 and this is n minus 1. So the power should be n minus 1. The n minus 1 is going to be k. This is going to equal k. The n minus 1 is k. Bring the 1 over. N is k plus 1. The n is being replaced with k plus 1. We have x to the r. The summation is k goes from some number to infinity. We'll find out that number in a moment. But n is k plus 1. We have k plus 1 plus r. K plus 1 plus r. And then you have 4n. Well, if I multiply the n by 4, I get 4n. If I multiply that by 4, I get 4k plus 4. So 4n is 4k plus 4. There's the 4k. I didn't write everything for the 4n yet. Plus 4r. And we have 4 from here minus 7 halves. Now 4 is 8 halves. Minus 7 halves is 1 half. Another way is 4 take away 3 and a half gives you a half. Either way we do it, we get a half. C sub n becomes k plus 1 times x to the k power. After all, we said n minus 1 becomes k. Now, what does k start with? There's two ways of doing it. When n is 0, first value of n, the first value the index takes on, then this will be negative 1. So I want this to be negative 1 initially, and that's when k is negative 1. Another way of doing it is, we know that n minus 1 is k. Well, if n is 0, because that's what it starts with, well, 0 minus 1 is negative 1. So k starts at negative 1. However you get it, get it. Plus the summation as n goes from 0 to infinity of Cn x to the k. Ck x to the k. K or n became k. N becomes k. Now, in this summation, in the sum of these two summations, they both have x to the k. But since their summations are not the same, we're going to leave it as x to the k. We're not going to factor it out. Let me erase the top. Now, you look at where the subscripts start. -1 and 0. 0 is the higher number. So I want to break off all the terms that are less than, where k is less than 0. Remember, this thing equals 0. So 0 is equal to x to the r times, I'm going to let k be negative 1. Negative 1 plus 1 is 0, times r is r, times negative 4 plus 4r. So there's the 4r. Now, negative 4 is negative 8 halves, plus 1 half is negative 7 halves. K is negative 1, so that subscript is 0, times x to the negative 1. Now, this mess is supposed to be added up where k is negative 1 and 0 and 1 and 2 and 3, etc. Well, we just dealt with negative 1. So now I can add on all of these in one shot. I can say the summation as k goes from 0 to infinity of k plus 1 plus r, k plus 1 plus r, times 4k plus 4r plus a half, times c, k plus 1 times x to the k, plus the summation k goes from 0 to infinity of c and x to the k. So 0 is equal to x to the r, this isolated first term, plus summation. Now, when it comes to these two summations, they both are summing over the same values. So I can add them up as one summation. And they even have x to the k in common. So the summation of k plus 1 plus r times 4k plus 4r plus a half times ck plus 1 plus c sub n. And I factor out the x to the k. Now I want this to equal 0. Now, x to the r is never 0, unless x is 0. But x can take on many values. I want it to be identically 0. So, either this is 0, that's 0, and each of these are 0. Because if we have the summation as k goes from 0 to infinity of 0 times x to the k, well, 0 times x to the k is 0. So you have 0 plus 0 a lot of times, an infinite number of times. You're gonna get 0. So it's enough for this to be 0 to make this whole summation 0. And so we want both of those to be 0. Okay? And we don't care what C0 is. And that's never going to be 0 because that's 1 over x. For a fraction to be 0, the top has to be 0, and it's not. So r times 4r minus 7 halves should be 0. So either the first factor is 0, and that occurs when r is 0, or the second factor is 0. And if you subtract two quantities and you get 0, you write down the two quantities and you put two horizontal lines in between them. But if you subtract two quantities and you get 0, because they were equal. So 4r is equal to 7 halves. It's very, very friendly to divide the left side by 4 to get r. But it's not friendly to divide a fraction like 7 halves by 4. But an alternative for dividing by 4 is to multiply by the reciprocal, and you get 7 over 8. So those are the two values for r. Okay, so I'm going to write 0 and 7 over 8. I'm going to write this a little bit higher. So r is equal to 0, or r is equal to 7 over 8. Very important. Now, we have the other piece that always has to equal 0. This equals 0. You want to solve for the one that has the larger exponent. Sorry, the larger base for c. K plus 1k. This is larger. We want to solve for this ultimately. So let's solve for the term that has the ck plus 1. By passing that to the other side as negative ck. Now if we divide both sides by that product, then we'll just have ck plus 1. So we have to do the same to the other side. And that is what ck plus 1 is going to be. But you know what? I hate that it's ck plus 1. I'd rather know what ck equals. I'm going to make every k 1 less. So ck is equal to negative c. Make the k 1 less. 1 less than k plus 1 will be k plus r. Now we have 4k, so it's 4k minus 1 plus 4r plus a half. So we have 4k, we have plus 4r, and now we have minus 4, which is negative 8 halves, plus the half, which is negative 7 halves. So we have 4k plus 4r minus 7 halves. And that's the rule that we have. But that rule is independent of what r is. Just because I'm going to use that rule twice, I want to write it down. ck is equal to negative ck minus 1, k plus r, four k plus 4r minus 7 halves. And r is 0 or 7/8. Well, if r is equal to 0, we get c sub k is negative ck minus 1. R is 0, so that's just k. And r is 0, so 4r is 0. Times 4k minus 7 halves. Multiply by 2. Multiply the numerator by 2. Multiply by 1, I meant to say, by 2 over 2. Now when you have a product like 7 times 5, and I say to multiply by 2, there's many ways of doing this. You can say it's 2 times 35 or 70. Or you can multiply the 2 and the 7 first and multiply that by 5. 14 times 5 is 70. Or you can multiply the 2 with the 5 first. You get 10 times 7 is 70. All ways give you 70. But whatever you do, you don't do 2 times 7 times 2 times 5. You don't do 14 times 10 or 140. You only multiply this number by one of those numbers in there. Of course, this will be completely different if it were addition or subtracting. Then you have 14 plus or minus 10. But if this is multiplication, only multiply one of those numbers by 5, or multiply by 2, or multiply the product by 2. Now when I multiply the bottom by 2, and this is why I chose to multiply by 2, I'm going to multiply that by 2. So I'm still going to have k. Well, 2 times 4k is 8k minus 2 times 7 halves is 7. I wanted to get rid of that fraction, the 7 over 2. So this is what ck equals when r is 0. When r is 0. Now, the reason I like to have ck here is because when I write down c1, that means k is 1. If this would have said ck minus 1, then, well, for c1, what is k equal? Oh, k must be 2, because 2 minus 1 is 1. No. For me, that's too complicated. I want to know what c sub k is. So when I write down c1, that means k is 1. So k is 1. You get negative 2 times c0, 1 minus 1 is 0, over 1 times 8 times 1 is 8, minus 7 is 1. You get negative 2c0 over 1 times 1. I'm going to leave the 1 times 1. Okay. Now, c sub 2, that means k is 2, is negative 2, c, 2 minus 1 is 1, over k, which is 2, times 8 times 2, 16, minus 7 is 9. So you get negative 2 times 9 times c1. Basically, I'm saying is that times c1. But c1 is this. So it becomes plus 4, or 2 squared, c0 over, I'll put the 1 first. 1 times 1 times 2 times 9. That is what c2 is. Now c sub 3 is negative 2, c sub 3 minus 1 is 2, over k, which is 3, times 8 times 3 is 24, minus 7, 17. So you have negative 2 over 3 times 17 times c sub 2, which is 2 squared c0 over 1 times 1 times 2 times 9. So you get negative 2 to the 3 c0 in the top, and in the bottom you get 1 times 1 times 2 times 9 times 3 times 7. Now hopefully you're seeing a pattern. When it comes to the numerators, I notice that the signs oscillate. It's negative, and then positive, and then negative. Well, if it starts off negative, I'll say negative 1 to the n. Because when n is 1, negative 1 to the 1 is negative 1. Negative 1 squared is positive. And then I noticed we have 2 to the 1, 2 to the 2, 2 to the 3. we have 2 to the power. Oh, when the subscript is 1, the power is 1. When the subscript is 2, the power is 2. When it's 3, the power is 3. So when the subscript is n, the power is n. Now in the bottom, don't worry about the second number in each bracket. We have 1, 2, 3. Well, when it was 1, we stopped at 1. When it was 2, we went 1, 2. When it's 3, we said 1, 2, 3. So when it's n, we're going to have 1, 2, up to n. What about the second numbers in each bracket? Well, if you multiply this number by 8, and you take away 7, I'm getting that from here, you get that number. If you multiply by 8 and take away 7, you get that number. If you multiply by 8 and take away 7, you get 17, excuse me. Just like I had over here. Just like I had right there. 3 times 17. 3 times 17. It's always whatever that number is times 8 minus 7. And that number, the last one, is always the subscript. So it's going to be 8n minus 7. 1, 9, okay. So that is C sub n. I'm just going to move the numerator more in the center and that'll be done. Negative 1 to the n times 2 to the n. That is what we get. When r is 0, we have C sub n is equal to negative 1 to the n. Well, I'm not going to have room to put it there. But basically, that's what we get when r is 0. Now what about if r is 7 over 8? Remember, there was our rule. So what we have is C sub k is equal to negative C sub k minus 1 over k plus r. So we have k plus 7 over 8 times 4k plus 4r. Well, if r is 7 over 8, and I multiply by 4, get 7 over 2. 4r is 7 over 2. So that's going to be 7 over 2 minus 7 over 2. I'm done. There it is. So to write it down a little bit more nicely, I would just say that this is negative ck minus 1. I'll just write the 4k in front. K plus 7 over 8. Now, if I multiply the bottom by 8 and the top by 8, that's allowed. I have negative 8 c sub k minus 1 over 4k times 8 times that is 8k plus, let's say plus, 8 times 7 over 8 is 7. Okay, one last thing. The 4 goes into the 8 2 times. So I get negative 2 c sub k minus 1 over k times 8k plus 7. So let me just write that down, and then we'll crank out the c sub k's. It's negative 2 ck minus 1 over k times 8k plus 7. let's find out what the first few c sub i's are, c sub n's are. C sub 1 would be negative 2 c sub 0. Oh, this is times c sub 0 over k, which is 1, times 8 times 1 is 8, plus 7 is 15. So that is c sub 1. Now, c sub 2 is going to be, well, that's when k is 2. 2 minus 1 is 1. So we get negative 2c1 over k, which is 2, times 8 times 2 is 16, plus 7 is 23. Now don't cross off the 2's. So we have negative 2 over 2 times 23 times c1. Now in the past, I wrote the equivalent of c1 being that. I really should have said times c0. So now I have positive 2 squared c0 over, I'll write 1 times 15 first, and then 2 times 23. And hopefully you start to see a pattern. The signs are alternating, negative, plus, so it's going to be negative 1 to the n, and then we have 2 to the 1, 2 squared. The power always is the same as the subscript, so it's 2 to the n c0, and when it was 1, we stopped at 1. When n was 2, we started with 1, and we went all the way up to 2. Well, when now the subscript is n, we're going to start at 1 and go to 2, all the way up to n. And the second value is always 8 times the first, over here, 8 times the first value, 8 times 1, plus 7, 15. 8 times that number is 16 plus 7, 23. And 8 times that number plus 7 is 8n plus 1. So that is c sub n. Let's call this c sub n1 for r1, and for r2, we'll call it c sub n2. So let's get rid of some of my side work. Now we know that y is equal to the summation of cn x to the n plus r, which is the same as the summation of cn x to the n times x to the r, as n goes from 0 to infinity. Well, the x to the r has nothing to do with the n's, so I can factor that out in front. For example, I couldn't factor out x to the n because it changes. When n is 0, and then 1, and 2, and 3, x to the n changes. But x to the r does not. Okay. N equals 0 to infinity. Now notice, I never said what c sub 0 is. That is, I'm going to break off the first term. First, I plug in 0 for n. I get c sub 0 times x to the 0. But x to the 0 is 1. So c0 times 1 is c0. Plus the summation that then goes from 1 to infinity of x to the n. But you know what? Let's call C01. Let's call C01. So we don't even need those C0s. Okay. So now, see what we can do here. So now, we have two solutions. We have y1, that's when r is 0. And remember, oops, this should be c sub n x to the n. When r is 0, this is 1. So I don't need that. y1 is 1 plus the summation as n goes from 1 to infinity of cn1 of this. Negative 1 to the n times 2 to the n times 1 times 1 times 2 times 9 all the way up to n times 8n minus 7 times, so far I just wrote down the summation of cn, now I have to write x to the n. That's one y value. And another y value, called a y2, is going to be 1 plus the summation as n goes from 1 to infinity of this c. Negative 1 to the n times 2n over 1 times 15 times 2 times 23 times n times 8n plus 7 times x to the n. And the one thing I didn't write in front was x to the r, where r was 7 over 8. Now, the general solution is a linear combination of the two solutions. We have 2 solutions. It's going to be, let me not use C's. It's going to be A1 times Y1 plus A2 times Y2. Where, of course, Y1 is all of this, and Y2 is all of this. Okay, that completes the first one. These problems, I said from the beginning, are long and tedious. Let's consider another one of these type problems. Again, suppose that x equals 0 is a singular point, and we want to find two linearly dependent series solutions about x equals 0. Now, quick comment is right there is just x. That means x minus 0 to the n. That's said to be a polynomial or a power series about 0. Same argument over there. We have x to the n, which is x minus 0 to the n. Now suppose we have 9x squared y double prime plus 9x squared y prime plus 2y is equal to 0. Now the first thing I'm going to say is I need to write that smaller. And we're going to try the same form solution as before. We're going to say that y is equal to the summation of Cn x to the n plus r. So then y prime is going to be the summation of n plus r, Cn x to the n plus r minus 1, and y double prime will be the summation of n plus r times n plus r minus 1 times Cn times x to the n plus r minus 2. Now I want to rewrite this using the new ways of writing y prime, and y double prime. And notice it equals 0. So 0 is equal to the summation. Now I can put the 9x squared inside the summation. Well, I put the 9 in, and the y double prime has an n plus r factor, an n plus r minus 1 factor, c sub n, and that factor. When I multiply it by x squared, I'm just going to get x to the n plus r plus 9x squared times y prime. Well, there's the 9, and this is y prime minus 1. So when I multiply by x squared, I'm going to add 2 to that power. It's actually going to become plus 1, n plus r plus 1. And then we have to add on 2y plus the summation. I'll put the 2 inside. Cn x to the n plus r. In fact, to save some space, please, let me write it up there. We don't forget plus that. Now, the only powers of x's that are the same come from the first and the third summation. In fact, that's in common. Oops, that's in common. So we have 0 is equal to the summation, and I can write it down as one summation. Remember, n is going from 0 to infinity for both of them, plus 2 times Cn x to the n plus r plus this one, the summation of 9 times n plus r Cn times x to the n plus r plus 1. And n is going from 0 to infinity. N is going from 0 to infinity. Now, I can factor out an x to the r by just doing this. So the new power at the end will be n plus 1. The new power here is just n. Let's clean this up in here. What is n plus r times n plus r minus 1? And then I'll multiply by 9 and add 2. Well, think of this as one piece, and that is 2 pieces. So when you do that product, you're going to get n plus r squared. And then you take away n plus r. And then you add 2. So you have 9 times n squared, I'm just squaring this, n squared plus 2nr plus r squared, take away n, take away r, and then add 2. And the question is that going to get you anywhere? Is that any simpler? No terms are canceling out, etc. Okay, so it doesn't look like the simplification we did down here was really simpler. So what I'm going to do now is I'm going to get the powers to be the same. I'm going to get them both to be k. Well, to let n equal k, that's easy. N will just be k. But over here, we're going to let n plus 1 equal k. So the first summation does not, well, it does change. N just becomes k. N becomes k. So we have x to the r. Make that r look believable. X to the r times the summation as k goes from 0 to infinity of 9 times k plus r times k plus r minus 1 plus 2 c sub n x to the k plus the summation as k goes from some number to infinity. Well, if n plus 1 is k, that means n is really k minus 1. So we're going to have 9 times n, which is k minus 1 plus r. Just wrote the plus r first. C sub n, well, n is k minus 1, and n plus 1 is k. Now, k equals n plus 1. Well, if n is 0, and that is what n starts off with, so 0 plus 1 is 1. That is, k starts with 1. Or, if you prefer, if k is first 0, then the first power will be 0 plus 1, which is 1. I want this first power, which is the same as that power, to be 1. Just let k start at 1. Okay. Close bracket because everything's being multiplied by x to the r. Now, when you look at the k's, they start at 0 and 1. 1 is larger. So I want to break off all the terms that are where k is less than 1. Namely, just when k is 0. So you have x to the r times, when k is 0, you just get 9r times r minus 1 plus k is 0 plus 2. And k is 0. C to the 0 times x to the 0, which is 1. I won't write the 1. Okay, plus, now, k goes from 1 to infinity. And so does it here. I can write this down with one summation. K goes from 1 to infinity. And that n right there, remember n became k? So that should just be c sub k. And the x to the k can be factored out. So I have the summation of this piece, 9 times k plus r times k plus r minus 1 plus 2 plus this 9 times k plus r minus 1 c sub k minus 2. I do have one little error here. That should be times c sub k. And x to the k gets factored out. Now, this is supposed to equal 0. One way out is if 9r times r minus 1 plus 2 times c0 is 0, and that's 0. 9 times k plus r times k plus r minus 1 plus 2 c sub k's plus 9 times k plus r minus 1 c sub k minus 2 is equal to 0. Those are the two ways to get out of this. Okay, which means we could erase an awful lot. Okay. When is 9r times r minus 1 plus 2 equal to 0? Plus 2 times c0 equal to 0. Well, we're going to let c0 equal 1 anyways. So we want 9r times r minus 1 plus 2 equals 0. So we have 9r squared minus 9r plus 2 equal to 0. That's A, that's B, and that's C in the quadratic formula. So r is negative b, which is 9, plus or minus b squared minus 4 times a times c. Now, 81 is 9 times 9. Well, this is all over 2 times 9. Now, if you have 9 nines, and 4 times 2 is 8 times 9, and you take away 8 nines, you're going to be left with 1 9 or 9. And after all, if you had 9x minus 8x, everyone would say you have 1x, or x. I'm just telling you that x is 9. Okay. So what's under the radical sign is 9, and the square root of 9 is 3 over, I'll say 18. So you get 9 plus 3 over 18, and you get 9 minus 3 over 18. 6 goes into the top and bottom number 2 and 3 times. Same 6 goes 1 and 3 times. So those are your r values. R is equal to 2/3, and r is equal to 1/3. Those are the two values for r. Now we go into the other formula, the other piece that must equal 0. 9 times k plus r times k plus r minus 1 plus 2 times c sub k, that must equal to 9 times, plus 9 times k plus r minus 1 c sub k minus 2. That must equal 0. So we want to solve for the smallest subscript of c. That is, we want to solve for this. Actually, we want to solve for the y distance. So I'm going to bring this to the other side. So this unfriendly number of c sub k's is equal to negative 9 times k plus r minus 1 c sub k minus 2. And if I divide by what I just crossed off, well, it cancels out on the left side, so I crossed it off, and it does not cancel out on the right side. So this is what c sub k equals. Now, I'm going to need that result twice. One for r equals 2/3 and one for r equals 1/3. third. R equals 2/3. R equals 1/3. And C sub k is good because it says k, doesn't say k plus 1 or k minus 1, is equal to negative 9 times k plus r minus 1 times c sub k minus 2 all over 9 times k plus r times k plus r minus 1 plus 2. So what happens when r is 1/3? If r is 1/3, c sub k is equal to negative 9 times k plus 1/3 minus 1. 1/3 minus 1 is minus 2/3. C sub k minus 2. On the bottom we have k plus r. R is 1/3 times k plus 1/3 minus 1 is negative 2/3 plus 2. Okay. So let's clean this up a little bit. I'm going to take, remember this is 3 times 3. I wrote down the negative 3 and I'm going to distribute that 3. And I get 3k minus 2. I wanted to multiply that by 3 to get rid of the denominator. Now this 9, I'm going to think of the 9 as 3 times 3. I'm going to multiply this by 3 and this one by the other 3. So I'm going to get 3k plus 1. 3k plus 1 times 3k minus 2. 3k minus 2. And do not forget to add the 2. Times that. C sub k minus 2. So C sub k is negative 3 times 3k minus 2 times C sub k minus 2. That product is 9k squared minus 6k. But then we add back 3k. So we only take away 3k. And then we take away 2. And we add it back. Okay. In the bottom, I can pull out a 3k. 3 times 3 gives me the 9. K times another k gives me the k squared. Minus 3k times 1. 3k times 1 gives me 3k. And the top is negative 3 times 3k minus 2. C sub k minus 2. And those 3's cancel. So C sub k is negative 3k minus 2 times C sub k minus 2 all over 3k minus 1. That is when r is 1/3. Let me put this way up on top and we'll figure out what C sub n is. So we have, that's what ck is. It's negative 3k minus 2 times C sub k minus 2 over 3 times k take away 1. And this is all when r is 1/3. Okay. Now, remember, we did the summation of C sub n x to the n plus r, and n started at 0. That is, the smallest subscript to C is 2. So it is 0, is 0. The smallest subscript is 0. So if I let k be 2, we're okay. Because I want k to be at least 0, and the other subscript, k minus 2, to be at least 0. That is, k has to be 0 or above, and adding 2 to both sides, k must be bigger than 2. If I'm thinking of a number that's 0 or more, and it's 2 or more, you should conclude that it's 2 or more. I mean, fair enough, 1. If k is 1. That is bigger than 0. Yes, it is. But you have to admit that 1 is not bigger than 2. But you want and. You want both to be true. So k must be at least 2. Okay. So c sub 2 is equal to negative 3 times. So k is 2. 3 times 2 is 6. Minus 2 is 4. C sub 0 over 3 times 2 is 6. Minus 1 is 5. That is c sub 2. C sub 3. Oh, no, I want to write c sub 3 over here. C sub 3 is negative, so k is 3. 3 times 3 is 9, minus 2 is 7, c sub 1. Over 3 times 3 is 9, minus 1 is 8. That's c sub 3. C sub 4. It's negative. 3 times 4 is 12. Minus 2 is 10. C sub 4 minus 2 is 2. All over 3 times 4 is 12 minus 1 is 11. So this is really negative 10 over 11 times C2. But C2 is negative 4/5 C0. So it's 10 times 4 over 11 times 5. Times C sub 0. So let me just write that down closer. It's 10 times 4 over, I'll say 5 times 11. I'll even say the 4 first. 4 times 11. That's C4 times C0. Now, C sub 5 is, so k is 5. 3 times 5 is 15, minus 2 is 13, minus 13. 3 times 5 is 15, minus 1 is 14. 5 minus 2 is 3. So it's negative 13 over 14 times C3, which the line above tells us is negative 7C1 over 8. So we get 7 times 13 times C1 over 8 times 14. And I'm going to put that right here. Seven times 13 C1 over 8 times 14. I'm hoping that you're noticing that when the subscripts are even, they're all going to be multiplied by C0. And when the subscripts are odd, they're all going to be multiplied by C1. So C6, that means k is 6, is negative 3 times 6 is 18 minus 2 is 16. And here we have 3 times 6 is 18 minus 1 is 17 times C4. So C4 is right above. It's negative 16 over 17 times C4, which is 5 times 11, 4 times 11 over 5 times 11. So it's negative, I'll just reorder, 4 times 11 times 16 over 5 times 11 times 17, C0. That's C4 in that bracket. Okay, so let's write that down. It's negative 4 times 11 times 16, C sub 0, over 5 times 11 times 17. And of course I have an error. 3 times 4 is 12 minus 2 should be 10. Sorry. So this just should be 10. Oh, but we're doing the bottom. It is 11. Excuse me. These differ by 6 and those two differ by 6. For some reason I thought they weren't differing by 6. Let's look at C sub 7. C sub 7, so K is 7. 3 times 7 is 21. Take away 2 is 19, negative 19. C sub 5 over 3 times 7 is 21 minus 1 is 20. So C5 is 7 times 13 times C1 over 8 times 14. So what we get is, rearranging their order, we get negative 7 times 13 times 19 times C1 divided by 8 times 14 times 20. 8 times 14 times 20. So let me put that down. We have negative 7 times 13 times 19 over 8 times 14 times 20 times C1. So now, let's see if we see a pattern for the even. 2 sub 2n. Well, what I notice is, goes from negative to positive to negative. So it's negative 1 to the n. And then I have, there's a typo here. That should be 2. I have 4 times 10. I have 4 times 10 times 16. Well, when n is 1, that will be 2. So right now, n is 1. How do we get that number 4? How do we get that number? When 2n is 4, that means when n is 2, how do we get the 10? When n is 3, how do we get the 16? Okay, how do we get this number? Or we can call these numbers 2n. Well, if I multiply, so first I start off with 4 and then 10, etc. And how do I get the last number? How do I get the last number? The answer is whatever k is, you multiply it by 3 and take away 2. Okay, and of course I meant to put those numbers on top. You have 4 and then 10, etc. And then it's going to be 3 times 2n minus 2. And in the bottom, it's going to be 5 times 11 times 17. And then ultimately, it'll be 3 times 2n minus 1. C sub 2n is going to equal to what I just said. The signs are alternating. You're going to have 4 times 10 dot dot dot, and then it's going to be 3 times the subscript minus 2 times C sub 0. So all times by C sub 0. The bottom will be 5 times 11 times 17 up to 3 times the subscript 2n minus 2. Of course, you can call that 6n minus 2. Except it shouldn't be the same as the top. It's 3 times the subscript minus 1. Should be 6, can be written as 6n minus 1. That is C sub 2n. Now, what about C sub 2n? Well, is it plus 1 or minus 1? Have to be careful with that. Now, when n is 1, 2 times 1 is 2, plus 1 more gives me C3. So we'll keep it as 2n plus 1. Now, what I notice is it's minus, plus, minus. Alright, negative 1 to the n. Then it's 7 times 6 more, times 6 more. Keep adding 6. Oh, 7 times, 13 times, etc. Now, how do you get the last number on the bottom? You multiply that subscript by 3 and then take away 1. So it's 3 times the subscript minus 1. Of course, you can call that 6n plus 2. That's what the top is going to be. 3 times 2n plus 1 minus 2. And those are multiplied by C1. The bottom is going to be 8 times 14 times 20. Notice they always differ by 6, all the way down to 3 times the subscript minus 1. So, we have our answer. We have two linearly independent solutions. Well, actually, that's only when r is equal to a third. This is only when r is equal to 1/3. Now, when r is equal to 2/3, we have that c sub k is equal to, now I'm going to plug in 2/3 for r. So we get -9, I'm reading this, and I'm going to say 2/3 for r is -9 times k plus 2/3 minus 1, which means minus a third. C sub k minus 2 over 9 times k plus r, which is 2/3, times, well, this happens to be the same as that. And you can do the arithmetic again, just make sure you get the same answer. Now, I want to multiply the top by, I want to multiply this by 3. So, that's the same as -3 times 3 times this, times 3 times this. And 9 is 3 times 3, times this times that. So, already multiply 4 numbers. I'm thinking of this as 3 times 3. Let's do that. 3 times 25 times 4 times 3. The order you multiply is up to you. I'd rather say it's 100 times 9 and not spend time and run to get my calculator, because time is important and we want it to take a shorter length of time. This is 3. 9 is 3 times 3. So one of those two 3's I multiply by this. And the other 3, 3 times 3 is 9, gets multiplied by the k minus a third. So I have -3 times this, which is 3k minus 1 over 3k minus 2. And I did forget to add the plus 2. In the bottom, this product will be 3k plus 2, and this will be 3k minus 1 plus 2. So I have -3 times 3k minus 1 times 3 sub k minus 2 over 9k squared minus 3k plus 6k is plus 3k minus 2, and then when you add 2 they cancel. So we're almost there. In the bottom, I can factor out as 3k. 3k times 3k gives me 9k squared. And then 3k times 1 gives me 3k. And then this 3 cancels. So there is your answer. -3 times k minus 1, c sub k minus 2 over k times 3k plus 1. Let me write that down up here. It's -3k minus 1 times c sub k minus 2 all over k times 3k plus 1. So the same argument as before, the lower subscript can't be 0, but be below 0. Nor can the larger one. But if the lower one is 0 or above, so will the larger one. After all, this number is 2 more than that value. Okay, so now if we have C sub 2, that's when k is 2, 3 times 2 is 6, minus 1 is 5, C sub 0 over 2 times 6 plus 1 is 7. That is C sub 2. Let us do C sub 4. So k is 4, negative. 3 times 4 is 12, minus 1 is 11, C sub 2. 4 minus 2 is 2. Over k times 3 times k is 12, plus 1 is 13. So it's negative 11 over 4 times 13 times C2, which is negative 5C0 over 2 times 7. So we have positive 5 times 11 C0 over, I'll say 2 times 7 first, times 4 times 13. Don't multiply out, because then you will not see your pattern. It's 5 times 11 C0 over 2 times 7 times 4 times 13. Now if you're slick and you're starting to catch on, you can see the pattern. The signs are alternating, so it's negative 1 to the n. We have 5 in both of them. Then we're going to have 11 in all of them, etc. Well, where does it end at? Well, if you triple this number and take away 1, that's where it ends at. If you triple this number, that's where the numerator ends at. If you triple that number, you get 12 and take away 1, that's where it ends at. So it's going to go all the way down to triple the subscript, which is n. Sorry, it's 2n. Going to triple the 2n, and then you're going to take away 1, and it's times C sub 0. Now, what about the bottom? Well, it's going to be 2, and then 4, and then 6, and 8. You have 2 times some number. You have 4 times some number. Eventually, you'll have 2n times some number. Now, what's the second number? What are the 2 and the 4, etc. being multiplied by? The answer is you triple that first number. The first number is that. You triple the first number and add 1. You triple the 2 and add 1, you get 7. You triple 4 and add 1, you get 13. You triple this number, you'll get 6n, and then you add 1. And there's C sub 2n. Now, what about the odd ones? What about C sub 3? Well, again, we go back to this famous rule. We triple the 3, we get 9. We take away 1, it's 8. C sub 1 over k, which is 3. We triple 3, which is 9, and we add 1. Don't reduce the 8 over 10. That's going to kill you. Now, C sub 5 is negative. The k is 5. 3 times 5 is 15, minus 1 is 14, times C sub 5 minus 2 is 3. In the bottom, we have 5, because k is 5. Then we have 3 times 5 is 15, plus 1 is 16. So it's what's in the bracket times C3. So it's what's in the bracket. Oops, should be a 5. It's what's in the bracket times C3, which is negative 8C1 over 3 times 10. The negative times the negative is positive. 14 times 8, I'll just write the smaller number first, times C1. In the bottom, I'll write the 3 times the 10 first, and then the 5 times the 16. Now, when it comes to C sub 2n plus 1, let me just write C sub 5 up here. We worked it out in the bottom. There it is. It's 8 times 14 C1 over 3 times 10, 5 times 16. Now, if you notice, the terms before stay in the game. The 8 over 3 times 10. It doesn't leave. In C7, in part of C7, you're going to have 8 over 3 times 10. You're also going to have 14 over 5 times 16. And then you're going to have another fraction. It's going to have another fraction. 3, 5, 7. They keep going up by 16. By 6. It's going to be 23. Keeps going up by 6. It's going to be 20. Or if you like to do it, remember, it's 3k minus 2 negative over 3k minus 1 times ck minus 2. Well, if this is 7, 3 times 7 is 21 minus 2 should be 19. Okay. We need to do our arithmetic a little bit better, folks. The 14 is wrong, and so is the 16. When I plug in 5, 3 times 5 is 15 minus 2 is 13. 3 times 5 is 15 minus 1 is 14. It's actually going up in the top by 5. They're going up by 5. 13 plus 5 is 18. And you can verify that. Why am I having a hard time here? Okay, let's not worry what we're adding. What we do know is we always multiply for the top this by 3 and take away 2. So what happens is if I have C sub 2n plus 1, we're going to have 8 times 13 dot dot dot. I'm going to triple the subscript. I'm going to triple it. And I'm going to take away 2. I'm going to triple the subscript and then take away 2. And that's C1. And in the bottom, I have 3 times triple that number and take away 1. 10. Then 5, the next odd number. Triple it and take away 1. Triple it, you get 15, take away 1. And then you triple the last subscript, 2n plus 1, and you take away 1. That's C sub 2n plus 1. Okay. So when r is equal to 2/3, there are my two pieces. There are my two pieces. Okay. So now, what does, for example, let me just put this line here. What does, for example, r 1/3 equal? Well, it's x to the k times 1. I'm letting C0 be 1, plus the summation as n goes from 1 to infinity of, well, what I'm going to do is, see, what happened is, we have n goes from 1 to infinity of whatever. But you know what? I want to go from the odd numbers. I want to first add the odd numbers and then the even numbers. I'm going to add the odd numbers and the even numbers. So it's going to be the summation of 2 sub n plus the summation of 2 sub n plus 1. Because first, if n is 1, I'm going to get C2 plus C3. 2 times 1 is 2, C2. 2 times 1 is still 2, plus 1 more is 3. Plus, now n is 2. 2 times 2 is 4. 4 plus 1 is 5. And this is working like a charm. Okay, it works like a charm. And remember that, okay, so now it's the summation of C sub n x to the n. So it's going to be C C sub 2n x to the 2n plus C times C sub 2n plus 1 x to the 2n plus 1. Okay, so C sub 2n is this mess. Now, I'm not going to write it, okay? What I just wrote in this bracket is literally this. Except C1 is 1. This is C sub 2n times x to the 2n plus C sub 2n plus 1, which is this. I really should write that, but I'm not. Times x to the 2n plus 1. That is one complete answer. Now, another complete answer is when r is equal to 2/3. I'll just call it y sub 2/3. It's x to the 2/3 times 1 plus the same exact stuff. N equals 1 to infinity of C sub 2n x to the 2n plus C sub 2n plus 1 x to the 2n plus 1. There's the answer. The only difference is I don't want you to think those are the same, so maybe I'll just call these C2n star and C sub 2n plus 1 star. Okay. Instead of this, you really should write that. And instead of this, you really should write that. Okay, that completes the second and final problem in this section. lots of alphabet soup, lots of places to make rather silly, careless mistakes. But understand the pattern and don't make silly mistakes like I do a lot. Okay, good luck with it. Thank you.